Here we go. 8. Let's go to 8 here. So 8, yeah, 8 is going to be a little long. But what's that first thing it tells you to do? What's that first thing? What should you do to the denominator? Yeah, you factor this right here. You factor this, and then your first goal is to get to this right here. That's your first goal. After you factor, you need to multiply by. Oh, look, you can go straight to the LCD. You just have to be careful what you multiply and how you multiply. You have to be careful what you multiply and how you multiply. So if you take this thing right here and you multiply it by this one, what cancels? What cancels between these two? The n plus 3. So you're just left with this. Then, if you multiply by the next one, what cancels? The n minus 1, and you're left with this. And then you need to make sure you multiply properly. Where do you think the most common error occurs on these lines? Line 1, 2, 3, 4, 5. Where do you think it happens? 2. Did I say that's 2 or 1? Yeah, that's 1. Going from 1 to 2. Where do you think the error is most common, going from 1 to 2? Condensing. When you multiply this out, it's minus all of this. It's not minus just the first one. So you see that bracket put around it? So the most common error, people would have a minus 9 there, not a plus 9. Yeah?
Yeah, that's that.
There, hey, go ahead.
I multiplied just the whole thing by n squared plus 2n minus 3. Like, is it okay that I just write it out?
It's fine, as long as you know it's factored.
Yeah.
You just took this and you knew that it's that. Sure. I mean, I'd rather you write out the factor form,
Okay.
just to be more explicit, because I could tweak those numbers by 1 and make it way different, and then you could assume it's factorable and it's not, and then you go as long as the remaining.
I mean, I just checked if it was factored.
That's fine, but you could literally write that. If you're checking it, you're doing as much work as writing the factor form. Yes.
When we do it with problems like this with complex denominators, are they always going to be factors of the larger equation?
You mean like, is this always going to be represented there?
Yeah.
At least partially, probably,
Yeah.
but not. No, it's not a guarantee. Like I could give you something that gets really big, but here's the limiter here. You know how to factor quadratics, and you know how to factor very, very limited cubics, right? What's the only way you know how to factor cubics right now? Grouping, right? We're going to learn some new ways to factor today, but right now, I can't go much higher than this because you have no way to like start climbing that mountain. You're looking at it going, I just don't even know what the first step is. We're going to learn some of them today that are very powerful, but right now it's generally going to be quadratic, definitely cubic or lower, and then anything higher than that will be like a specific pattern for later. What's the key to number 10? You see two things that are squared. What can you do to both sides? Square root. When you take a square root, you have to have two cases though. So you have this thing equals positive 5 or this thing equals negative 5. You have to do both cases. You have to do both cases. That's the key. Because if I said what squared is 25, the answer to that is 5 or negative 5. So then you get two answers here, you get two answers here. So how many answers are there? Plus or minus 9 and plus or minus 4. You just have to do both cases. That's it. I highly recommend not multiplying this out. Some people might do that, and like, why do the fourth? Whenever you're going into lands of polynomials that are higher than squares, maybe cubics or fourth degree, make sure that's absolutely the right place to go. Things can get really nasty if you get the powers higher. You get really nasty. Like, not cool. Because look, what you're going to get if you do this out, you're going to get like, y to the fourth, 25, y, you know, like y, oh, it's not going to be good. Did you try doing that? Yeah. You're like, hey, like, there it is. So the key is recognize squares. Yeah. That's about it.
I should know.
No, it's fine. I mean, it could be worse. Like, any of these could be worse. Yeah. Any of them could be a lot worse. Factoring takes something that's big and breaks it down into individual pieces. What's the other direction?
Something small.
Bigger, so that'd be multiplication. So factoring is one direction, multiplication is the other direction, depending on which way you want to point first. Which one is generally easier? What's generally easier, multiplication or factoring? What's generally easier? Generally. What?
Multiplication.
Multiplication is generally easier. Generally easier because there's one algorithm you can run that runs rather quickly, right? So factoring can be really challenging. You need more tools. We're going to give you more tools today. So what did I say at the beginning of this class? Well, hopefully you'll have quadratics or cubics, but sometimes you're going to have to factor things like this. That one's a little more fun because what's the power of that polynomial? What's the highest degree? 4. And the thing is, you might try grouping, but is grouping going to work on that thing?
Why isn't grouping going to work immediately? How many terms are there? There's 5 terms, and like you have to make a common term by pulling things out. There's like no easy way to do that, right? But here's the thing. We know that x squared plus 2 is a factor. So let's say I told you, everybody, let's say I told you that 1, 2, 3, 6, 18 had, I don't know, I'm making this up. This is definitely a bunch of numbers multiplied together, right? At least 2, right? Let's just say I told you 52 divided evenly into there. Let's say I told you 52 divided by evenly into there. How would you find the other factor? How would you find the other number that multiplies by 52 to get 123,618? You'd use division, right? You would take this number, divide it by this, and what would you get? You'd get that. So what do we need to know how to do? Polynomial. Oh. Polynomial long division. It runs very similarly to regular long division, and I'm not too confident you remember all your long division, but we're going to review it by doing this. The setup is exactly the same. We want to know when you divide x squared plus 2 into x to the 4th plus 3x squared plus 2x cubed plus 4x plus 2, we want to know what you get out. We want to know what you get out. Anybody want to guess what the first thing we need to do is? Before we do any actual math, we need to put something into the thing we're dividing into.
Wait, isn't it also out of order?
What'd you say?
Isn't it out of order?
Is it out of order? Did I write it properly? Okay, so that's that could be the first step. Sure. Wait, did I write it wrong? No, I wrote the same thing, but you want to put it in order. So let's write it in order. So if we write this in order, what are we going to get instead? Yeah, plus 2x cubed plus 4x plus 2. Is that in order? Are all the powers represented? Yeah, 4, 3, 2, 1, 0, right? X to the 0. The first thing you need to check is, are all the powers represented? Let's say there was no 3x squared term there. What should I write if there was no 3x term?
0x.
0x squared. 0x squared is 0, so are you adding anything if you add 0x squared? And no, it's a placeholder that makes this algorithm doable. How many people have done polynomial long division before? A couple people? So the only phrase you need to remember, really this is the only thing you need to remember to be successful at this, is leading over leading. That's what you need to remember. Leading over leading. What is the leading term here? What's the leading term on this? So what you do is you do the leading term of what's underneath. So x to the 4th over x squared. What does that equal? So where did that come from? That came from that x squared is there, and that x to the 4th is there. And where do you put this now? Where do you think you put that? On top, and you can keep it in order. I like keeping it in order. It is x squared. After you put a number up there, you might remember from regular long division, what do you do with this x squared once you put something up there? What do you do with it? Multiply by x squared plus 2. So when you multiply by x squared plus 2, what do you get? X to the 4th plus what? 2x squared. Do you see how I wrote that underneath the right power?
Wait, why'd you put x squared above?
Because leading over leading is x squared, so you put it there. I'm giving you an algorithm. This is what you do. You do leading over leading. What you get, you put it there. Why did I put it there? Because I want to keep it in order. It helps keep track of it. Instead of putting it over here and having gaps, I just like keeping track of it. So do you see how I then, when I multiply, x squared times x squared is? X squared times 2 is 2x squared. What do we do now? Do you remember? Anybody remember? Subtraction. And before you subtract, please put a parentheses around it. Again, what do you think the most common thing people get wrong when they do this algorithm? They don't subtract properly. So what is x to the 4th minus x to the 4th?
0.
Oh, and what is, there's 0x cubed here, so what do you end up with?
2x.
2x cubed plus x squared.
Where'd you get the 2x squared? Plus 4.
We are subtracting these two things from this entire thing. That's what we're doing.
Well, where did you get the 2x?
X squared times x squared is x to the 4th. X squared times 2 is 2x squared. There it is. Are we okay with what I have written up there?
Yeah.
What's the phrase you need to remember? It's not on the board anymore. What's the phrase? Leading over?
Leading.
What's the new leading term on the top? So what do you have now? 2x cubed. This leading term stayed the same. What do you end up with?
2x.
2x. So you end up with 2x, so plus 2x. What do you do with this 2x now? This 2x went there. What do you do with it? By the x squared plus 2. And what do you get? 2x cubed plus 4x. And what do you do? Oh, it's the same thing over and over again. What do I put around this? Please put parentheses and then the minus. What's 2x cubed minus 2x cubed? 0. So what do you end up with? X squared. Oh, and there's a 4x here, by the way, because you can drop that down. Plus what? What's 4x minus 4x? 0. Plus 2. You can do that, absolutely. What's the new leading term? So what do you have now? X squared over? What's x squared over x squared? Where do we plug that 1 in? Up here. So it turns into plus 1. So then you get x squared plus 2. And when you subtract, what do you get? Is it a very good thing we got 0?
Yeah.
If we didn't get 0, we would have known we did something wrong. Why?
It can't be remainder.
Exactly, because we know x plus 2 is the whole definition of something being a factor is it divides evenly. You need 0. This whole section is going to be called really the search for zeros. Really. Because if you find something like, oh, that's actually helpful. So what does this tell us? It tells us that x squared plus 2 times this is equal to that thing. So what do we now know? Based on what we just did, we now know this. We now know that x squared plus 2 times x squared plus 2x plus 1 is equal to x to the 4th plus 2x cubed plus 3x squared plus 4x plus 2. You just factored a 4th degree polynomial. You just factored a 4th degree polynomial. That's 4 right there. Ah, great question. I was going to ask you that. Theoretically, everything is factorable. Power 2, power 3. It is factorable. Are they guaranteed to be nicely factorable? No. They're absolutely not guaranteed to be nicely factorable. Are either one of these nicely factorable? Yeah. One of them is. Which one? Yeah, so if I asked you to fully factor this, this stays x squared plus 2. What does this turn into? X plus 1 times? So you could write it as x squared plus 2 times x plus 1. This would be the fully factored form that I would be looking for right there. That right there is the awesome final answer. The whole key to this was that you were told something is a factor first. So what could you do? You could then do polynomial. What's it called? Long division. Okay, I will keep this up on the board. Find a piece of the board with somebody you're not sitting next to, and please do the bottom one. I'll keep that right there so you can copy it down first. So I saw a lot of great things here. What's the fully factored form?
X plus 2.
What do we get here? X squared plus 1. You first got this, right? X squared minus x minus 6. But then what does it turn into? X what? Minus 3 times x plus 2?
Yeah.
Nice. Oh, yeah, it is frozen. Thank you. It turns into this. So if I asked you to fully factor this, given a factor, that would be the answer. What's the key thing though here? What's the key to this whole, your whole ability to get to this? What was the key piece of information? If I didn't give you that that was a factor, where do you start? You now have a tool to divide. You have a tool to divide, but you need to know what to divide by. This is nice. This is effectively, this is a 4th degree, but once you factor it, once you pull something out, you get back to something you really like, which is a quadratic. So there's a second thing here. It's this. How many people have seen the phrase, those 2 words right there? Anybody seen synthetic division before? One. Now there's just 1. We got a half, 3, 4. Oh, there's more. Excellent.
I think I like that way better.
It is. Here's the key. Why couldn't we use synthetic division on the ones we just did?
Because the factors were squared.
Yes. If you were dividing by, or if you need to divide by something that isn't linear, so you see it's squared right there, you have to use polynomial long division. I'm going to show you a method that makes this whole thing a lot faster, but it only works with linear factors. X minus 2, x plus 5, 2x plus 3. It only works with lines. So if you can get a line or a linear term that you want to divide into something, you can use this method. Here's how it works. First thing you do, and again, this is synthetic division. The first thing you do, you make this little symbol. It's like the opposite of the division sign. Opposite of the division sign. Then you ask yourself, what makes the factor 0? What makes that 0? What makes this 0? What makes that 0? You take that and you plug it in out front, right there. So that's where this goes, right there. Next, you list the coefficients in order of what you're dividing into. Anybody remember what that's called, what you're dividing into? It's the kind of thing you learn in 5th grade and then you forget immediately. What? Is it the quotient? I think it's the quotient. It's the divisor, the remainder. I think it's the quotient. What are the coefficients?
1, -3,
-3,
-14, 12,
and 40. Now, I brought this up at the beginning last time. What happens if it skipped a power? What happens if there was no 3x cubed there? What would you have to put in? You gotta put in 0. You have to put in 0. Have to. First step after you list out the coefficients is you drop the first number down. So I'm going to drop this first number down and get 5. Just like with polynomial long division, you're going to do the same thing over and over again. You're now going to multiply by the green number. What's the green number? What's 5 times 5? What do you do with the -3 and 25? Do you remember? You add them, and what do you get? What?
I have a question.
Yeah, go ahead.
Don't you drop down the 1?
Oh, I dropped down 1 and wrote 5. You're absolutely right. It's totally my mistake there. What do you do with these two numbers? Mm-hmm. Then what do you do? The same thing over and over again. Multiply by?
5.
10. -4. Then what? Negative. Come on. 20.
Wait, hold on. How do you multiply by? Multiply by 5, multiply by 5, multiply by 5. It's always multiplying by this number right there. It's always multiplying by the same number, and you add every single time.
So I add this, and then I get what? Negative what? -40, and I add them together, and what do I get?
0.
You are going to get so programmed to love the number 0. That right there is a happy thing because you have verified that it is a factor. I'm generally not going to lie to you. If it says it's a factor, it should come out to 0. So if you did this and it doesn't come out to 0, what does it mean?
That's not a factor, true.
Either it's not true or you made a mistake somewhere in here. Okay? So if I tell you something is a factor and the synthetic division doesn't come out to be 0, you need to check your work. What you just did is you evaluated this polynomial at 5. When you plug 5 into this polynomial, guess what you get out? 0. And that's the same thing as x minus 5 being a factor. X minus 5 being a factor is the same thing as being able to plug in 5 into the whole polynomial and getting out 0. But here's the super helpful part. We now know that x minus 5, we verified it's a factor, but guess what's left? How the heck did I get that? Where the heck did this come from? Where does it come from? Chris, where did it come from?
Yeah.
What?
The expression of it.
Yeah, look, there's the -8, there's the -4, there's the 2, and there's the 1. The cool thing about synthetic division is that these numbers are the coefficients of the remainder. They're the coefficients of the remainder.
And then we'd have to group.
Well, hold on. Now, let's just pause here for a second. We've factored out one term from a quadratic. So we've gone from a quartic to a cubic, right? So what did we start with today? I gave you a factor that wasn't linear, gave you a factor that is linear. We pulled it out now. Now we're at a cubic, right? But what was the key to this whole thing? Again, different process. But what was the key? If I didn't tell you x minus 5 is a factor, did you have any way to start this? No. So now I ask the question, what about this? We might want to try what? Let's try grouping and see what happens.
But if it's a factor of the larger equation, wouldn't it still be a factor of that equation?
No. Just because this is a factor of the larger does not mean it's a factor of the middle. It could be there multiple times, but not necessarily. I mean, think about it this way. Is 7 a factor of 21?
Yeah.
But is 7 a factor of 3? No, not necessarily. So let's try grouping. Does grouping work? Does grouping work? What can we factor out of the first two terms here?
X squared.
So what do we have here? X squared times x plus 2. Then what should I factor out of the other one? Careful. Minus 4 times x plus 2. And does grouping magically work on this one? You get x minus 5 times what? Oh, and then can you keep on factoring? X minus 5, x plus 2, x minus 2, and x plus 2. So if you're going to write this final form, there it is. At this juncture, when you got to this line, what is your only plan of attack at this point? Grouping. Because what have I not shown you yet? If you don't have a factor to begin with, or a potential factor, how do you find a list of potential factors? It's not about finding the factor straight off. If you could do factors quickly, you would solve one of the hardest math problems there is. It's more of a universal constant. This is the constant. Factoring is hard. If factoring wasn't hard, there'd be no such thing as encryption, effectively. We'll talk about that later. But at this point, if I said, use synthetic division on this, what would you say? Well, with what, right? What are the potential zeros? So we want to know what are the potential zeros. What are the potential zeros?
Why do you use 5 in that one? 0.
So what you're looking for there is you want to factor that, right? Because you want to factor it so that you can find what each factored thing equals 0, and then you can solve. Your goal is to factor. So I'm going to teach you something super powerful, which is the potential rational zeros theorem. Has anybody seen this before? No. Listing potential. Oh, gosh, it's something that's new, maybe. So here's how you find the potential zeros. First, you make sure it equals 0. It does equal 0. And then you look at the leading coefficient and the last number. Yeah. Okay? Everybody with me so far? The leading and the last. It should be a constant. If it's not a constant, factor out the x. What are all the factors of 10? What are all the factors of 10? 1, 5, and 10. And then what did I put up in front?
And 2.
Oh, and 2. I forgot a whole section of them, too.
And then you just try to synthetic.
Hold on, but we're not quite there yet. What's the leading coefficient?
1.
And what are what's the factors of 1? Just plus or minus 1. Your favorite leading coefficient will continue to be 1, everybody, okay? Now you write all of the possible fractions that look like this. Can someone list for me all the possible fractions? 1 over 1, 2 over 1, 5 over 1, and 10 over 1. What happens if instead of 1 we had the number 3? What? You would have twice as many, right? Because in addition to 1, what else would you have? 1 over 3, 2 over 3, 5 over 3, and 10 over 3. How many potential rational zeros are there? Careful. How many?
8.
8, because it's plus or minus. This tells us there are 8 potential rational zeros. There are 8 of them. What does that mean? Literally what those words state. If this has rational zeros, meaning if it has rational numbers that make it 0, they'll be in that list. So what do you do with each of those numbers? Well, not guess and check. What do you use? Synthetic division. You test them until you find one that comes out to be 0 with synthetic division, right? So here's the deal. Each of these numbers has an equal chance of being the 0, but is it easier to deal with fractions or larger numbers or smaller numbers or whole numbers? Which ones are easiest? Smaller whole numbers, right? So if this was 3, I told you the list could be twice as long and have thirds in it. Check the easy numbers first. So what number should we check first?
1.
Let's just check 1. So if we check 1, what are the coefficients, Noah? 1, 1, what's the next one? Negative. And 10. And then we're going to test 1. Drop the 1 down, multiply by 1, you get 1. 2, 2, -5, -5, -10, and? Hey, look, did it come out to 0? Awesome. So if, over here, Chris, x plus 3 was a factor, so what was the 0? -3, right?
Yeah.
If 1 is the 0, what's the factor? What's the factor?
Oh,
X what? Yes. And then what's left? Can someone tell me what's left? The coefficients are right there. Can you tell me what's left? Lindsay, tell me what's left. Right there. What's left? What does that turn into right here?
X to the third.
Yeah, you have to kind of go right to left and count. X to the third plus?
2x squared.
Mm-hmm.
Minus 5x.
Minus?
Minus 10.
-10. Hey, we just factored out the first term. We just factored out the first term. Technically, has the degree gone down 1? Yes. Now, though, what do we have to do again? The same thing. Hey, did our set change, by the way? No. And can you have the same thing again? Could this be a 0 again?
Yeah.
It could. So what should you start with again? 1. What are the factors? What are the coefficients now, Arvin? What are the coefficients now?
1.
Mm-hmm.
2, -5.
So what do we end up with? 1, 1, 3. Well, hold on. We can't. I just want to continue it just to see what happens here.
Why are we not grouping that?
Again, just answered that 2 seconds ago. I want to continue this way and then verify it with grouping, okay? 3, -2. Does it work?
No.
Always check, though. When you do potential rational zeros, you're going to test a bunch of these. And what are you going to tend to want to do after you get one that doesn't work? Erase it. Do not erase them. Why? You could have made a mistake. Let's check it. 1, 3, that works. Hey, okay, so 1 doesn't work. We could test -1, right? Let's test -1. What's that going to be? 1, 2, -5, -10. Who wants to tell me the numbers? Drop the 1, and then what are the rest? Arvin, go.
-1.
Yep.
So 1 times -1 is -1. And then -6.
Mm-hmm. Mm-hmm. And what? So this is not what we want. Neither one of those is a 0, right?
Yeah.
So we tested 1 and -1. What should we test next?
I'd say
We have the list right there.
2.
So let's say 2. So we got to here. Let's test 2. 2, 1, 2, -5, -10. Alex, can you tell me what the numbers are going to be?
Oh, yeah. 2, 1.
2. Mm-hmm.
4.
Mm-hmm. What is it going to be?
-3.
Well, it's going to be it's 8 there first, right?
And so it would be
-3?
-3. Sorry, 3.
3.
6.
And then what? Hey, we're still, it seems frustrating, but we're knocking them out here.
-2.
Let's try -2 and see what happens. So -2, 1, 2, -5, -10. David, can you tell me this one?
1, -2,
Mm-hmm.
0,
Yep.
0,
Mm-hmm.
-5,
Mm-hmm.
+10,
And?
0.
Hey, is that what we wanted?
Yeah.
So what does that now tell us? If this is a 0, what's the factor? X plus 2. So pause at this section and go, okay, what do we now know? It factors into x minus 1. Where does that x minus 1 come from? The first one, right there. And what do you have left? X plus 2, and then the coefficients are right there. X squared minus 5. Technically, you could factor that would still be real numbers. Anybody want to factor x squared minus 5 for me? Anybody? This is the difference of squares. X plus? Yeah, you do. What's the square root of 5? Yeah.
Oh, yeah.
You could do that. Can you tell me the 4 solutions now? We now know if this is equal to 0. Someone tell me, raise your hand and tell me the 4 solutions. Natalie.
1, -2, and then -3.
Yes. You have all 4 right there. The key to this, though, was this right here. You see this list? That list is awesome because how many numbers are in it?
8.
There's only 8. Could the list be longer?
Yeah.
Yeah. Which ones do you test first? Small and easy ones. Small and easy. Yes, Alex.
Well, like, what if you tried to, like, do this thing with something that can only be factored by a quadratic?
What do you mean? Say that again. So now Noah's like, okay, I'm done. I'm just like mic dropping it out of here because what scared you away at that point, Noah?
The 6x squared minus 7 minus 5.
Yeah, you should try to factor it. It's not that fun, but you should try at least, right? So how about 6x and what? Is it 6x or should I use 2?
I did 3x and 2x.
It's 3x and 2x?
3x minus 5.
Plus 1? Does that work? So, hey, this is why you get a whole group of people factoring and somebody gets lucky and gets it. It's nice. Use that skill. Make it fast. So do you know what the zeros are now? Can someone tell me what they are? Natalie, what are they?
3, 5,
And? Yes. The -1 comes from there, there. Thank you. -1/2. Thank you. There they are. Noah, how do you test if you're like totally stuck and you're not sure if that factors nicely? What do you do if you're not sure if it factors nicely? Do that. That's the discriminant of the quadratic. It factors nicely if that's 0. What's the b value on that shaded yellow? So what is that? 49. Oh, sorry. If it's a perfect square, so plus what? 24 times 5. That's 49 plus what? 100 and?
I thought it was -5.
It is negative. Oh, -5. But it's negative and negative. See, I made it positive because it's negative and negative. So what is it? 100 and? 20. What's that added together?
169.
What's the square root of 169?
13.
13. So if you get a nice number, 16, that is a nice number because it's 13 squared. It means it's nicely factorable. You could just use the quadratic formula if you really wanted to. If you just really wanted to.